So we've discussed a bit compact subsets of RG or general metric spaces. Now I want to go back to the case where I have a compact metric space or possibly a subset of a larger metric space, which is compact with its metric. I have a complete metric space Z, and I want to look at the space of continuous functions from K to Z. That's CKZ. We've looked at one specific case of that, which is when K is the interval 0, 1 of some interval AB in the real line, which we know is compact, and Z is just real numbers. Now we want to look at these things more generally. We're going to have this definition of a metric here that the distance of f and g is the sup of the distances of f of t and g of t for t in the domain of f and g. We still don't know that that's a metric, but we'll get to that. And but before, we want to descend, well, in the whole lecture, we're trying to descend properties of functions in this space, properties of the space itself. But I want to begin with something that's not about the space, that's just about individual elements here, there, which is saying that all continuous f from K to Z are uniformly continuous. And what does that mean? It means that for all epsilon, there exists a delta, positive, such that for all t and t prime belonging to K, if the distance in K between t and t prime is less than delta, that means that the distance in Z of f of t prime is less than epsilon. Right, so usual continuity says that you give me a t, you give me an epsilon, I have to find you a delta such that for all t prime, if the distance is less than delta, the distance between the values of the function is less than epsilon. But notice that I say if I give you a t and give you an epsilon, so the delta can depend on both epsilon and t in the usual definition. Here I'm saying something stronger. I give you an epsilon, and you have to find me a delta that works for all t and t prime that are within distance delta. So epsilon cannot depend on t. It has to be delta cannot be dependent on t. It cannot depend on t. It has to be the same delta given epsilon for all t. So for instance, if the domain of the functions is at the real line, we know that not all continuous functions are uniformly continuous. Say any differentiable function with a bounded derivative is not uniformly continuous. That's a simple exercise. But over a compact domain, over compact intervals of the real line, of course, we know that continuous functions are uniformly continuous. We're going to prove that a similar fact holds for all compact metric spaces, if that's a domain, right? So all elements of the space are actually uniformly continuous. How do we prove this? Well, there are various proofs, and some use subsequences, and I want to give a different proof. I want to give a topological proof. And the topological proof uses something about open covers of compact metric spaces, which we proved, right? So if A open cover of K, there exists a delta such that for all t and t prime K, if the distance between these guys is less than delta, then they both belong to the same ball. They both belong to the same set in the cover. So this delta is called the Lebesgue number for the open cover. This is something that holds for all covers, and we actually proved that this is true in the proof of the grand equivalence. We basically, in the proof of the grand equivalence, the end of the proof, I wanted to prove that if a space is such that all continuous functions achieve their minima and the space is totally bounded, then for any open cover, there's such a Lebesgue number. A radius that guarantees that for all points C and T prime at distance less than delta, then there is a single element in the open cover that covers the two. So we know this exists for that proof. Now, what open cover are we going to apply this to? I'm just going to say for all x in K, there exists a positive radius such that for all t and t prime in the ball around x of radius r of x, the distance between f of t prime is less than epsilon. And how do we know this? Look, fix an x in K. We know that f is continuous. That's our assumption, right? So I can always find the radius around x so that the difference between f of x and f at another point of the ball in the ball is at most epsilon over 2, strictly less than epsilon over 2, right? Just saying, okay, find me a radius that's small enough that guarantees that for any t in the ball, f of t minus f of x is less than epsilon over 2. So such a radius exists because f is continuous at x, at all x. Now, if the distance between f of t and f of x is less than epsilon over 2, then if I give you 2 points in the ball, the distance between f of t and f of t prime has to be less than epsilon, just by the triangle inequality, right? This is at most the distance of f of t to f of x, plus the distance of f of x to f of t prime. Okay, so for each x, I have a ball like this. The open cover is just a collection of these balls. So maybe you cannot read it here. Sorry. My open cover is going to be the collection of all these balls. Okay. Right, these balls cover K. Well, they're all contained in K. They cover K because for each element of K, I have a ball that covers that element. Therefore, all elements of K are covered. These sets are open, so this is an open cover. And therefore, there exists such a delta, right? So what does that mean? It means the following. There exists a delta such that if I give you two elements of K and their distance is less than delta, they belong to the same set in the open cover. That is, they belong to the same open ball. If they belong to the same open ball, the distance between f of t and f of t prime is less than epsilon. And then we're done, right? So oddly enough, this very abstract concept of Lebesgue number gave us exactly the result. To recap, we define an open cover where, given one element of this open cover, we guarantee that f of t and f of t prime, right? Given two elements of a set in the open cover, we guarantee that the distance between f of t and f of t prime is less than epsilon. This open cover is made of balls, but it doesn't really matter. It could be any collection of open sets that has this property. The point is that we do have an open cover. Therefore, it has a Lebesgue number. And therefore, if t and t prime at distance less than delta, they belong to the same set in the open cover, and the distance between f of t and f of t prime is less than epsilon. So this you could call as a topological proof of uniform continuity, except that uniform continuity really is a metric concept. It requires a metric for its definition. But okay, now we know that it's true. And now we're going to move on to something different. So this is a property of individual elements of CKZ. Now I want to prove something more general, but about the whole set of functions. And I want to prove that, as a matter of fact, it's more going to be like a sketch of a proof, because it's based on things that we already know. Which I have this definition here for any f and g, and as usual, I'm going to call my space C, right? My set of continuous function, I'm going to call C. I'm just going to say this C is a metric on C. DC is complete. So this is basically the same result that we proved over the space of continuous functions, except that there we didn't have a metric at first. We had a norm, which is in this infinity norm, and we proved that this norm makes C a complete vector space, complete norm vector space, that is a Banach space. Here we're doing it with a metric, but it's not much different. Okay, how do we prove this theorem? Well, first of all, we have to check that this is well defined, and in order to have a metric, it's necessary, for instance, that the sup is a real number. Therefore, I want to prove that this is bounded. Okay. So thing number one, I want to prove that for all f and g in C, this supremum is bounded. And what I'm going to note is that this function that takes t and maps it to distance between f of t and g of t, remember that f and g are fixed. I'm going to argue that this function is continuous. So, and why do I need that? Well, this is a function from k to r. And because k is compact, I know that all continuous functions are bounded and actually achieve the supremum. Therefore, the supremum not only is finite, but is achieved at some t star in k. So how do we show that? So, well, it really means that I want to prove that if I have Tn going to t, well, what do I have, right? So I have the distance of f of Tn, f of t going to 0. I have the distance g of Tn, g of t going to 0. And now I want to argue that the distance f of Tn, g of Tn minus distance f of t, g of t, this should go to 0. Well, this should go to this as a consequence of these two things. So it's more like I have a sequence of points. Sorry, this is not dc, right? This is dz. And how do we get this? Well, this is really a simple exercise. I'm saying basically I have the sequence x sub n converting to x. I have the sequence y sub n converting to y. And I want to prove that the distance of x sub n to y sub n converges to the distance of x to y. How do we do that? Well, just write something like this. D of x sub n to y sub n is at most, I'm just going to use a triangle inequality. I'm just going to say this is at most the distance between x and yn plus the distance from xn to x. So no big deal, just a triangle inequality. I'm going to apply the same inequality again. And then I get something like this. And these two things go to 0. And I can get a similar inequality if I have d of x to y, right? So I'm saying d of x sub n, y sub n is bounded from above by something that converges when it goes to infinity to distance of x and y. So the lim sup of that is at most this. I also have something similar, right? Just say distance from x to y is at most distance from x to yn, and then from yn to y. And now I break this again, and I want to have here the distance from x to y, and then I'm going to get, I want to have here distance of x sub n to y sub n. So I want to replace x with x sub n. I have to pay this price, and I have this. So now I have a different equation. This is the distance from x to y is bounded from above by the distance from x sub n to y sub n plus something that goes to 0. This implies that the lim inf of this is greater than this. So the lim inf is at least this thing. The lim sup is at most this thing. Lim sup and lim inf are equal. Okay, but this, as I said, is just a simple exercise, right? So I need to argue that the map that takes t to f of t, distance of f of t is continuous. And if if it's given that it's continuous, then it's bounded, achieves its supremum because K is compact. Okay, and what does this mean? It means it's a supremum is well defined and it's a real number. How do we prove that this gives us a metric, the supremum, right? So I'm just going to sketch very quickly. Well, you have to argue that this is symmetric. We have to argue that it's symmetric, but if I switch f and g, I switch f of t and g of t here, and the metric on z is symmetric. The distance is non-zero because these guys are non-zero, greater than 0. The distance is equal to 0 if and only if f of t and g of t are equal for all t, because that's the only way the supremum is going to be 0. And if f of t and g of t are equal for all t in the domain, it really means that functions f and g are equal. So the distance is always non-negative and is 0 if and only if f equals g. And finally, we have the triangle inequality, right? So which is just saying, okay, if I compute the distance between functions f and g, if I compute distance between f of g and g of t, I certainly have the triangle inequality, right? So I'm just taking f, g, h, and c. I certainly have the triangle inequality in Z. Right, so we've done this before. And this is at most, well, if I take the sup, this is for all t and k. So if I know the upper bound for this is given by dc of f and h plus dc of g and h. Now, this means that distance of f of t and g sub t are bounded by distance between functions f and h and functions g and h for all t. Therefore, this right-hand side that does not depend on t is an upper bound for the left-hand side. And when I take a sup here, the sup of this quantity has to be less than this. Therefore, dc of f and g is less than the sum of the distances, which is our triangle inequality. Okay, so that's part 2. And finally, we have to argue that this is a complete metric space. And basically what we're going to do is we're going to argue very similarly to what we did when we proved that C01 to R is a complete metric space. So I'm going to make this quick. Okay? How did we argue over there? So, okay, I have a sequence that's Cauchy in my space. And what does that mean? F sub n, F sub m goes to 0, and n and m both go to infinity. What we argued in that case is that if you have a Cauchy sequence to the sup norm, right? So this is like a sup metric, not a sup norm. But if you have a Cauchy sequence in that metric, then for all t, f sub n of t is a Cauchy sequence in Z, which means it converges because we assume that Z is complete, right? So, and how do we know this? Well, we know that the distance between f sub n computed at t and f sub m computed at t, this is less than the sup over t of this quantity, which is this c, fn, fm. This goes to 0 when n and m go to infinity. Therefore, this is sandwiched between 0 and something that goes to 0, which means that when n and m go to infinity, this also goes to 0. Okay? So, as I said, if this is Cauchy, always, then there exists f of t, the limit. And 3.2 is where we argue that in fact, I still don't know that f is continuous, right? But I'm going to argue that in fact, if I just define dc fn of f by the sup, right, or the need f to be continuous to define it like this, I have to have this thing go to 0, because as we did in that proof, we have that dc f sub n f is equal to the sup in t and k, and dz f sub n t f of t, and this is less than, well, remember that f of t is the limit of f sub m, so sup t and k lim in m dz fn t fmt, which is less than, okay, and now I need to say something like this. Okay, this is less than the distance between functions f sub n. Sorry, this is hard to see. So what we did in that proof is to say, okay, I'm going to take a sup over here in t, right? I can upper bound this by the sup. So I can just say the c f sub n and f sub m. Well, maybe you want to have a lim sup here, but the point is that when n goes to infinity, this limit goes to 0. And that I'm going to leave as an exercise. It's the same thing as the proof for continuous functions. So the last thing, and which I'm going to write here, is to argue that f is continuous because it's the uniform limit of continuous functions. And that is really the same thing. So if t sub n converges, t sub k converges to t, you look at the distance between half t sub k, half of t, and you follow the equations of that proof, then you can upper bound this by distance of f sub n of tk, f sub n of t, plus twice the distance. This is the distance in z, right? This is also distance in z. But this is the distance between functions with this abuse notation. I'm using it for f that I don't know yet that's continuous. You just follow those inequalities, and now you can take the k, limit in k, so you get the lim sup of this guy. This goes to 0, right? tk converges to t. F sub n is known to be continuous, so this goes to 0. And we deduce that the lim sup of this in k is at most twice the distance from f sub n to f. But this holds for all n, and then we can let n go to infinity, and we know this guy goes to 0. So the lim sup is bounded by 0. And that is a sketch of the proof that we have a metric space that is complete here. Okay. Now, there's one last thing that I want to mention, and I mean, I was already kind of fast with this, but I'm going to be even slightly faster with what I'm going to say right now, which is more like a remark that we're going to use later. So I'm going to switch over to the case where z dz is equal to v vector space and dz is given by a norm, such that this guy is Banach. So an element of C KV is a continuous function that assigns a value in V to each element of K. And you can, of course, define this metric, right? So this is a special case. We have a complete metric space that's V with the metric given by the norm. So we have a complete space, right? So, but what I want to mention is that this guy here is a vector space. And that it's actually Banach with some norm. So what kind of vector space is this? Well, it's very simple. So I want to add two functions, f and g, that belong to C. And what I need to do to add two functions, I need to define what the value of the sum is at any point t in the domain. And that's just saying, well, since I can add elements of V, since set f of t belongs to v, g of t belongs to v, then I can define the sum, right? This is a sum in v, if you like. Just like when we add functions with real values, we can add functions with vector values, values in the same vector space. And we can define a product by a scalar in the same fashion because we can take products of scalars by elements of v. So there's no mystery here in this vector space structure. Now, my main point is that I can define a norm of this space that makes it a Banach space, which is a sup in T and K of norm of f of t as an element of v. And this is the same thing if you use a definition, right? So it would be dz of f to the zero function, where the zero element here is a function that maps all elements of k to the zero element of v. Right, so you have the definition, and my point is that this is a norm, and because we know that the corresponding metric space is complete, CKV is a Banach space with this norm. We're not going to use this now for anything, but it's sort of nice, even if V says RD, then basically, I mean, this is not a big deal when it's RD, but it's still kind of interesting to consider sometimes functions that map compact sets, say even a compact interval of the real line to RD, which are like trajectories of ODEs, right? So you have a vector that lives in high dimensions, and the time associated with each point in time, a point in space. So we're gonna be considering things like that later, but that's it for now. Thank you.